So this is still 5-3. We're calling it day 2. So this is really just that second part of 5-3, so maybe the 5-3b. And we're still just working on solving equations, but we're going to probably get into a little bit more challenging ones with this. So when we look at this first example, and we have 2 sine squared plus 3 cosine minus 3 is 0, it looks quadratic, but the issue here is that the functions are different. So we're going to have to take a couple additional steps to maybe use a trig identity that we can substitute in to make it so it has the same function. So instead of having a sine squared, I'm going to substitute in the 1 minus cosine squared from the Pythagorean identity, and then say plus 3 cosine minus 3 equals 0. And so then now I just need to simplify that. So now I have 2 minus 2 cosine squared plus 3 cosine minus 3 equals 0. And if we simplify everything, I get minus 2 cosine squared plus 3 cosine minus 1 equals 0. So I'm going to look at this and I'm going to want to factor it. And I can do that now because the functions are the same. And I don't know about you, but I don't love when this leading coefficient is a negative. So what I'm going to do is actually multiply everything by a negative. So that way I have 2 cosine squared minus 3 cosine plus 1 equals 0. If it helps to do that substitution, so it looks just more familiar, we can let the cosine equal a. So we could say 2a squared minus 3a plus 1 equals 0. 2a squared will factor into 2a times a. We need a plus 1 and a minus 3. So we know that we're going to use 2 negatives. So we're just going to have -1 and -1. And then just do that quick check to make sure that when you FOIL it out, you get -3 as your middle term, which we do. So now if we set each factor equal to 0, we get that a is 1/2 and that a equals 1. But remember that cosine actually was our value, not a. So we have to figure out, when does cosine equal 1/2 and when does cosine equal 1? If we check back at the problem to see, we don't have any restrictions, right? We don't have that 0 to 2 pi, so we're going to have that plus 2 pi n on our answer. So cosine, again, those are your x values. Cosine is 1/2 here and here. So we would say when x is pi over 3 plus 2 pi n, and when x is 5 pi over 3 plus 2 pi n. And then cosine just equals 1 right here, and it only when you go around. So it's really when cosine equals 1. You could say when x is 0 plus 2 pi n, or you could just say 2 pi n. It means the same thing. All right, so when we look at this next one, with this equation, you have 1 plus secant equals tangent, and there's really just not a lot you can do with that. But if the tangent was tangent squared, then you could substitute in for secant squared minus 1. So what we're going to do is we're actually going to square both sides. So we're going to square this side, and we're going to square this side. And now remember, when we're squaring that left side, that's really like saying 1 plus secant times 1 plus secant. We can't distribute a square, and that will equal our tangent squared. So even just looking at this, before I FOIL out the left side, I know my function is going to be secant. So I'm going to substitute in for this tangent squared here in the next step from my formula sheet, and I'm going to use the secant squared minus 1. So if I FOIL out this left side, I get 1 plus 2 secant x plus secant squared x equals, and then I'm going to substitute in for tangent squared, of secant squared x minus 1. Right? So now we have all of the same functions, and now let's get them all to one side. So I'm going to subtract the secant squared, and I'm going to add the 1. And when I do that, right, so this side I have 0. If you notice this side, your secant squareds also become 0. So you just end up with 2 plus 2 secant x equals 0. And so now we just have to isolate that function. So we have 2 secant x equals 2, negative 2, or secant x equals negative 1. And here you might want to think about reciprocals. So you could say 1 over cosine equals negative 1, which means if you multiplied both sides by cosine, you would get that 1 would have to equal negative cosine, or that cosine would have to equal negative 1. So you need to think about, when does cosine equal negative 1, and we're not restricted. So cosine is your x-coordinate. It equals negative 1 over here. So we would say when x equals pi plus 2 pi n. So this next example is when we have multiple angles. And so what you'll notice in this next example is our functions, the sine or the cosine, won't just be x. This ku will mean we have like a sine of 2x, or we'll have a cosine of 3x, and we'll have to work on solving that, isolating the trig function first, and then using some inverse trig that we've worked on earlier in the year. So with this first example here, with the multiple angles, if we have 2 cosine 3t minus 1 equals 0, we're still going to start out the same way we have, where we try to isolate that trig function. So we'll say cosine of 3t 2 cosine 3t equals 1. So cosine of 3t equals 1/2. Okay. And so normally we would say, well, when does the cosine equal 1/2? And again, thinking about your unit circle, your cosine is 1/2 up here at pi over 3, and down here at 5 pi over 3. Right? So cosine equals 1/2 at pi over 3. We're not restricted, so plus 2 pi n. And at 5 pi over 3, plus 2 pi n. Okay? But normally we would be done, and that's what x would equal. But if you notice, instead of an x, or instead of a variable, we have 3 times that variable. So instead of saying x equals pi over 3 plus 2 pi n, we would say that 3t is at that point. Right? So whatever we were taking the cosine or the sine of is what we're setting that value equal to. So then to actually solve for the variable, we have to eliminate that 3 out front. So we have to multiply everything by 1/3. So here we would get t equals pi over 9 plus 2 pi over 3n, because we have to distribute that 1/3 to every part. Same thing for the second one. We would get t equals 5 pi over 9 plus 2 pi over 3n. Okay. So these problems, the only difference is adding an extra step when the middle term, when this term isn't just an x or a t and it has that multiple angle in front of it. Just make sure that you're setting your equation equal to that, and then simplifying that constant that's out in front. And then our last example just talks about using inverse functions, which we've kind of indirectly already been doing. So this is really just another example for us here. And again, if we're looking at it, it looks quadratic, but we have two different variables. So you have to think about, is there a way that you could substitute in for secant squared possibly and only have that tangent variable or that tangent function? And so we know from our formula sheets that secant squared is tangent squared plus 1. And then we would have minus 2 tangent. And let's bring this 4 over. So minus 4 equals 0 because we're just setting this up to be quadratic, to look quadratic. So we would get tangent squared minus 2 tangent minus 3 equals 0. And so here we have to think, does anything multiply? Because we have this leading coefficient of 1 right here. So does anything multiply to give us negative 3 and add to give us negative 2? So our tangent squareds will factor into tangent and tangent. And your multiples of negative 3 are negative 3 and 1 or negative 1 and 3. And if we need a negative 2, we're going to go with a negative 3 and a positive 1. So when we're solving these, we get that the tangent of x minus 3 equals 0, and the tangent of x plus 1 equals 0. So the tangent of x equals 3, and the tangent of x equals negative 1. Let's check to see if we're restricted, and we're not. But here's the thing is, up until this point, we've been adding plus 2 pi n because we had sines and cosines, or secants and cosecants, and their period is 2 pi. But remember that the tangent has a period of pi. So if we're going around, we're only going to be adding pi n. Right, so we have to think, when does tangent equal negative 1? So when our sine and cosine have a similar value but opposite. So that's over here at 3 pi over 4 and over here at 7 pi over 4. So we could say here x equals 3 pi over 4, right? But we're only going to add pi because that's what it would take us to get to the next one. So plus pi n. And then for this one, you don't know necessarily a value on your unit circle when the tangent equals 3. So on this one, you would actually do in your calculators the inverse tangent of 3, and that would give you your x coordinate. We're in radians, so make sure when you do that, your calculator is in radians. So if you do the inverse tangent of 3, we get x equals 1.249. And again, we still have to add that plus pi n.